For this lesson, we're going to be taking a look at some very important foundational principles from statistics. These are collectively known as measures of central tendency. And there are three common measures that you are probably familiar with in one way or another. And then we're going to branch off into some other fairly common uses, some very practical uses of them. The most common, the one that most people are going to be familiar with, is what's known as mean, which is also commonly referred to as average. In a mathematical setting, in statistics and in data management, we generally don't like to use the word average because it has some ambiguities associated with it. So when we're talking about a mean, that means what we're going to do is we're going to take all of the data that we have available and we're going to add it up and we're going to divide by the number of pieces of data. In statistics, we actually are a little bit more specific than that. It's not really going to affect us yet, but as we delve deeper into statistical tools, there is going to be a difference between population mean and sample mean. For now, for the calculations you'll be doing to start, they're indistinguishable from each other. The emphasis is really all you need to place in the back of your mind. When you do a population mean, that means that you have access to every single piece of data in the population. So if you were doing some sort of some sort of data collection on an entire school, you would have a data item for every student in the school. Then you could do a population mean. A sample mean would mean if you were doing an experiment on the students in a school and you were only going to sample specific 1 out of every 10 students selected randomly or specific grades, that sort of thing, then you are doing what's known as a sample mean. You are not sampling every single student, you're only sampling some subsection of those students. Okay, in either case, you can see the formula here looks very similar. This, for if you're not familiar with it, this is the Greek letter mu, which is traditionally used for the population mean. And then this, we would normally call this x bar if we were trying to describe it. Let's say we were trying to describe that over the phone. We would call that x bar, where x is whatever variable you're using. Traditionally, we use x, but this could be any variable that you've assigned to your data. And as I note here at the bottom, these calculations are identical, but we use different symbols, and later on in the course, it will actually matter whether we're dealing with a population or a sample. Now, this is something else that we've covered in the course, which is sigma notation. And sigma notation is used when you're taking the sums of things. So the simplest sigma notation would be this one. Here I'm saying I want the sum. That's what the symbol sigma stands for. So I want the sum as the variable, or what's known as the index. That's why we use the letter I. As the index changes from 1 to 4 in steps of 1. So when the index is equal to 1, well then I is just equal to 1. When the index increments to 2, I is now equal to 2, and we add that. And then it increments to 3, and we add that, and then it increments to 4, and we add that. We can also start to create more sophisticated expressions using sigma notation. Once again, I'm going to start at 1, and I'm going to increment by 1s until I reach 4. But now I'm not going to just take the I value, I'm going to take x subscript I. Now we use subscripts in mathematics to denote different terms. So this is basically saying I'm going to add the first term to the second term to the third term to the fourth term. Or another way of saying that is I'm going to take the sum of 4 terms. But if we go back and take a look at it, that's what averages are doing. That's what means are doing. They are taking the sum of a number of terms and then dividing by however number of terms you just added together. So in the case of the sample mean, then we would have x bar is equal to this part on the top So this part on the top is just what we had written before. It's actually the same as this part right here, except for it's extending out. So that would be x1 plus x2 plus x3 plus and so on until we reached the last value, which would have a subscript of n. So sometimes you might see this notation. Mathematicians are very fond of more condensed notations for things, even if it initially looks quite complicated. Now, another thing we need to talk about, and again, I think I'm laying groundwork here. When we talk about measures of central tendency, I just want you to understand what it is that we're measuring when we compare them. So, depending on how the data are organized, you can have these things that are called outliers. Outliers are pieces of data that don't fit in well with the other pieces of data. And that's generally going to happen with some frequency. You quite often, when you run an experiment, you get a piece of data that just doesn't fit in with the others. What becomes important is you need to understand that that can, what we call, skew the distribution of the data. So the distribution of the data is just the shape. If you put all of the data points into some sort of graph like this, the distribution of the data is what is the shape of that curve. This middle curve is symmetric data, and you can see that. You can see that along that dotted line, the data is symmetric. And in that case, all three measures of central tendency, I've only spoken about mean so far, we're about to look at median and mode, all three of them will be the same. If you have your data skewed to the left, then you can see that's going to have a big impact on mean. If your data is skewed to the left, your mean is going to get pulled in that direction. The median is going to get pulled a little bit, and the mode is always going to stay with the peak of the data. If it's skewed to the right or skewed in the positive direction, then the mode stays with the peak, the median is going to drift a little bit to the right of the peak, and the mean is going to get pulled quite a bit to the right of the peak. And so you can see here, the mean is affected most, or sorry, the mean is the one that is most affected by outliers, and the mode is the one that is least affected by outliers. So if you have outliers in your data set, and you want a better representative measurement of central tendency, if you can calculate mode, then that's probably your best bet. Now, there are other problems you run into. If you don't have very much data, mode is not a useful measure. And I'll talk about that in a moment when I talk about mode. So just a reminder, you should have learned these definitions and worked with these to some extent. The median is what we call the middle value. And so what it's basically saying is if you take your data, now it's important that your data is sorted in order to determine the median. You can't determine the median from an unsorted list of data. So the first thing you may need to do is sort your data, and then you find the middle. Now, sometimes there will be an exact middle. So for example, if I have the numbers 1, 2, and 3, well, 2 is exactly in the middle, so that's the median. But if I had 1, 2, 3, 4, well, the middle in that case is going to be between 2 and 3. And so when we have the case where we're between two values, and you can see that occurs when I have an even number of data points, in this case I have 4 data points, the median is the midpoint or the halfway value between those. So between 2 and 3, it would be 2.5. And the mode is the most frequently occurring value or values in the data. So if I do 1, 2, 2, 3, then in this case my mode is equal to 2. That's the most frequently occurring piece of data. If I do 1, 2, 2, 3, 3, 4, in this case, both 2 and 3 occur with a frequency, meaning how many times do they occur. There are 2 2s and there are 2 3s. So in this case, the mode would be equal to 2 or 3. or I guess we would say and 3, 2 and 3 are the mode of this data. They're both equally most frequent. So I did a couple of small examples there. Let's look at a slightly larger example. And in this case, we have a set of data, and you can see the first line that I give you is unsorted data. Now, this is kind of right on the edge of what you want to be doing by hand. To spare a little bit of time in this video lesson, I have organized the data. I've sorted the data already. And sometimes you'll just be given a question where the data is already sorted. So if you're given the raw data in an unsorted mode or an unsorted form, you have two options. You could sort it by hand. If you're going to sort it by hand, I recommend that you, as you start doing your sorting, you identify the smallest value, and as you write out those values, I look for any other ones, there are no other ones. The next smallest value is 2. So as you write out those values, you're going to eliminate them from your list so that you don't mistakenly write them out again. Now I look through, there are no more 2s. Now I look for, and for example, 3. And you can see I've got 3 3s and 2 4s, etc. So do be careful if you're doing something like this by hand. The other thing you have as an option, if you have quite a large set of data, is to use a computer. A simple spreadsheet, pretty much any standard spreadsheet that you're going to run into, is going to be able to calculate mean, median, and mode. You don't have to have the data sorted. It'll do that for you. And I may produce a small tutorial or link a small tutorial on how to do these calculations using a spreadsheet. Okay, so in this case, I've already sorted my data. It asks us to do mean, median, and mode, but we can do it in whatever order we want to. So why don't we go ahead and start with the median, since I've already focused on the idea of sorting data. If you take a quick look, what we have here is 2, 4, 6, 8, 10. I think I already lost count there. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. So there are 20 pieces of data here. That would mean the median is going to be at the halfway point, which is 10, but 2, 4, 6, 8, 10, is that right? Is right there. And then I've got 2, 4, 6, 8, 10. So there are 10 pieces of data here, and there are 10 pieces of data here. And since this is an even number, then the median is actually going to have to be halfway between those two values, which in this case are 5 and 6. So in this case, the median is equal to 5.5. What about the mode? Is there a single value that occurs most frequently? I already mentioned I've got 1 1, 2 2s, 3 3s. So I currently have 3 3s, 2 4s, 2 5s, 1 6, 7, 8, 9, 10, 12, 15. So it looks like those 3 3s are the mode. So the mode is equal to 3. 3 is the most commonly occurring value in my list. And then finally, the mean. So the mean, which in this case I'm going to use that slightly shorter notation, the mean is equal to, now we said we had 20 pieces of data, so that's going to be the sum. I'm going to need a little bit more room to write this. So x bar is equal to the sum as I goes from 1 to n, but in this case n is 20, of each individual piece of data divided by the total number of pieces of data. Or another way to put this is I'm basically taking all of the data. So 3 plus 4 plus 2 plus 8 plus, and I'm not going to write out all 20 pieces of data again, and then the last couple of pieces plus 10 plus 7. I would add all of those up and I would divide by 20. I don't always do this, but thankfully this time I have done this, which is the sum of the data points or the data values is 155. That's all divided by 20, and we end up with a mean of 7.75. So there is my mean, median, and mode for this data. Okay, now there's another type of mean that can be quite useful, which is known as the weighted mean. So sometimes we want to assign more value to a particular data point that we have. And this is something that most students are familiar with. We don't normally weight tests and quizzes to be the same. You don't normally weight your term mark and your final exam mark are often different, that sort of thing. And as a side note, so we're talking about this idea of weights, but while I'm doing this, I also just want to talk about notation, which is I often make the joke that mathematicians are a bit on the lazy side, and I don't know that I think that's a half truth, because a lot of the terminology or a lot of the notation can get quite tedious. So if you are, for example, taking the sum of all of the values in a particular set of numbers, you don't have to, at least not for me, you don't have to show the index every time. I may ask you specific questions where I say, make sure you use, if I ever say anything like proper notation, make sure you're filling in the indices. But when you're just doing your own work, homework, that sort of thing, or even most test questions, just do it as sums. Okay? Now let's look at this particular formula. So now we're talking about a weighted average. Of course, you would only do a weighted average or a weighted mean if you actually have weights associated with the values. And so what I do is I take the product of each weight times each data point, and I divide that by the sum of all the weights. So I add up all those products, and then I divide by the sum of all the weights. And let's see what that looks like in practice. Now I've made a very tongue-in-cheek example here. It doesn't work this way, and I actually don't feel this way, but I thought it would be a funny way to illustrate it. Imagine we have a student who's taking math, physics, chemistry, and biology. That's a pretty tough semester, and their results are 60, 70, 80, and 90. Now, if we looked at this from a pure mean perspective or an average, then what we would end up with, if we just looked at these marks, you can see the 60s balanced with the 90, the 70s with the 80. So this student would have a 75% average for those 4 courses. But I have done this very fictional weighting where I'm saying that math is worth 10 pieces of weight, whereas the physics is only weighted 5, the chemistry is weighted 2, and the biology is weighted 1. So what would that look like as in terms of a weighted mean? So the way we would do that, the weighted mean is equal to, it's going to be the sum of the weights times the data points. So what we would actually do is we would take 60 and multiply it. Actually, let's do it in the order they say. The formula says the weight times the data point. So the weight is 10, and then the data point is the grade in that particular course, which is 60. Plus, there's a weight of 5 times 70. Plus, there's a weight of 2 times 80. Plus, there was a weight of 1 times 90. And then I have to divide that by the sum of all the weights, which is 10 plus 5 plus 2 plus 1. And what we end up with here is, actually I didn't do this sum in advance. I've got the answer here under the green bubble. This one would be 600 plus 350 plus 160 plus 90 divided by 15, 16, 17 divided by 18. We add all of that up, and we end up with an average of, oh, that's not what I wanted. I wanted to move that. We end up with an average of 67%. So this is approximately 67. So that's what the person has for their weighted mean. So if we had done just a mean on those 4 marks, which is what you would normally do, you would have gotten a mean of 75. But because the math and the physics have greater weight in this calculation, they've actually dragged the mark down into the 60s. It's bad news for that student, unfortunately. They should have done better in math. Okay, and now what about something that's actually something very similar to a weighted mean? It's a very similar calculation. And it's when we have data that's not individual data, but it's grouped data. And the most common way to see group data is in something called a frequency table. So what we basically do is we're going to have data that has some sort of interval usually associated with it. And this is how we calculate that mean. Now this one, I don't think I want to talk it through. I think I want to show you. I think it's going to make more sense that way. So let's just go straight into the example of that. So I've got a frequency table here, and I have to determine the average number of hours spent watching television. So we have some sort of survey was done where children or the parents of those children was asked how many hours per, I assume this is per day, could be per week, but I'm going to assume it's per day. How many hours per day does your child watch television on average? And so they had one response that was from 0 to 1 hours, 4 responses from 1 to 2, 7 responses from 2 to 3, 3 responses from 3 to 4, 2 responses 4 to 5, and 1 response 5 to 6. So let's take a look at the how are we going to figure out what's the average number of hours? So the first thing we do is we make use of the middle of each interval. And so what I'm going to do is it's kind of like the weighted mean, because what I'm going to do is say from 0 to 1, this one child is going to, in that case, I'm just going to put that number of hours in the middle. So I'm going to treat it as if this one child watched 0.5 hours of TV. Now you might wonder why I'm doing that, but I don't actually know whether they watched 0 or 1 or a quarter of an hour or 3/4 of an hour. So I'm just picking the middle of the interval. So that's the first thing you need to identify. In this case, it's all quite simple because each of the intervals is simple. So the middle of each interval, I'm putting over to the side here. So there's the middle of each one of those intervals. Now the other thing I have to do, so M is the middle of each interval, so that's my MI. And now FI, well, that's the number of children, so that goes there. So if I want to, I could make another column, and sometimes it's a good idea to do this. I'm going to make another column MI times FI, or FI times MI. And what that does is say, it says take the frequency and multiply it by the middle of the interval. So 1 times 0.5 is just 0.5. 4 times 1.5 is 6. 7, now these are going to get more difficult. I think I can manage though. 7 times 2.5, well, 2 times 7 is 14, and then plus 3.5, so that one's 17.5. 3 times 3.5, 3 times 3 is 9, and 3 times 0.5 is 1.5, so that one's 10.5. 2 times 4.5 is 9, and 1 times 5.5 is just 5.5. Now, from there, we have to add up all of those FI, MIs. So I can go to the bottom here, and I can just add these up. And again, that shouldn't be too onerous a task. I normally like to start with my larger values first and get them out of the way. So I've got 17.5, which becomes 18, which becomes 28. And then I've got plus 9, so that's going to be 37. And let's go ahead and finish this off down here. So 37 plus 5.5 is 42.5, 48.5, 49. So I end up with MIFI when I add all of those up together. So this is equal to the sum of MIFI. And I also need the sum of all the frequencies. Well, that's going to be this column. So the sum of the frequencies is 5 plus 7 is 12, plus 3 is 15, 17, 18. And so that is the sum of all the Fi values. And now that I have those, I can simply calculate my mean for this frequency table. And so the mean is equal to the sum of MIFI over the sum of Fi, which is 49 over 18, which works out to be, and I have a calculator here because I didn't calculate this one in advance, 2.7. So the average number, or the mean number of viewing hours, based on this data, we can't be super precise, but based on the data that we were given, is about 2.7. And does that make sense? Well, the maximum number of viewing hours, or sorry, the maximum frequency was in the interval between 2 and 3. So 2.7 makes sense, and we take a look at the data, how many are on one side, how many are on the other side. And so that does seem like a reasonable answer. And that's it for our various measures of central tendency. Mean, median, and mode are the core of this, and then we have other calculations we can do. Generally, the other calculations are going to be involving the mean, a variation on the mean calculation. And that's it for this lesson.